In today's lesson, we shall be looking at solution to first order partial differential equation using the method of characteristics. And today we want to look at semi-linear PDEs. Semi-linear PDEs. If you haven't yet subscribed to the channel, kindly hit on the subscribe button for me. And I believe at this very point, we know what semi-linear PDEs are. So when we say that a PDE or a first order PDE is a semi-linear PDE if the non-linearity is on the U. What makes the PDE non-linear is on the dependent variable U. So you can see that the higher derivatives within the equations, they are all linear. Us is linear, Uy is linear. But what makes the PDE non-linear is what the transcendental function on the dependent variable U. So this makes it non-linear, and since the non-linearity is on the U, this becomes what? A semi-linear PDE. So how do you solve a semi-linear PDE using the method of what? Characteristics. So that is what we'll be looking at in today's lesson. We are going to look at some few examples, and then we see how best we can go through them. So kindly stick and stay with me. So let's look at this particular example. We want to solve for x greater than 0 of this semi-linear quadratic problem SUX plus YUY is equal to x e exponent negative u. Very easy. We are going to follow the same approach that we used when we were looking at the linear PDEs. So first, we are going to find our A, our B, and then our F from the equation given, and then we form our characteristics equation. So from the equation, our A is the coefficient of what? Ux, that is what? X. And then RB is the coefficient of Uy, and that is what? Y. And then RF is the function on the right hand side of the equal sign, that is x e exponent negative u. Now once we have this, we form the characteristics equation, which is giving us dx all over A is equal to dy all over B is equal to du all over what? F. Very, very easy. So this characteristics equation is going to reduce or convert this PDE into an ordinary differential equation. And once we have it in ordinary differential equation, we can make use of any method that we know in solving ODE to solve this particular equation. And we can even use our simple integrating techniques. So let's plug in this. We have our dx all over our A is what? X all over dy all over B is y, and then du all over what? F x e exponent negative u. So as I said earlier on, when f is not equal to 0, we are going to have two equations. When f is 0, we form only one equation, but when f is not equal to 0, we form two equations. So it means that we are going to form two equations from this characteristics equation that we have formed. So we have our first equation. So with the first equation, let's pair this and that, okay? So we are going to pair dx and then what? Dy to give us our first solution. So we are going to have dx all over x is equal to dy all over what? Y. Very, very easy and then simple. Now you can see that the variables have already been separated, so we are just going to what? Integrate both sides. So we have the integral of that, and then we have the integral of that. When we integrate 1 over x dx, we are getting what? Ln of what? X. So we are going to have ln x. Then we add the constant of integration. Since we are having ln, let's also add ln c1. So when we integrate 1 over y dy, we are also going to get ln what? Y. So we have ln y. Very good. Now we want to make c1 the subject. So let's bring ln x to the right hand side so that we'll be left with ln c1 is equal to ln y minus what? Ln x. So we have len C1 is equal to len. We apply our basic knowledge in logarithm. Since they are subtracting, we have len and len. We can pick one of the len and then we divide their argument. So we have y all over what? X. So we have len C1 is equal to len y all over what? X. So we are looking for C1, not len C1. So what do? We take the y on both sides. So we have y and then that, so that this will cancel this. We are left with what? C1 is equal to what? This you also cancel the len. We have y all over x. So we have our first solution, and our first solution is what? C1 is equal to what? Y all over x. Very, very easy and then simple. Once we are done with the first part, we move on to the second pairing. So with the second pair, we are going to pair du with any of this, either du with dy or du with what? Dx. Let's take the one that is more convenient. You can see that when we pair dy and then du, it will be very difficult to use the separation of variable because of this what? X. So let's pair dx and then what? Du. So we have second equation. Dx all over x is equal to du all over x e exponent negative u. Now we want to separate the variables, right? So why don't we multiply both sides of the equation by x so that we can cancel this x or do away with this very x. So multiplying both sides of the equation by x, we are going to have x dx all over x is equal to x multiplying du all over x e exponent u. We want to separate the variables. That is why we are multiplying both sides of the equation by what? X. So that this x will cancel this x. And then this x will cancel this x. So that we'll be left with what? Dx is equal to du all over e exponent negative u. So we have separated the variables and therefore we can integrate straight away. So we have the integral of this and then the integral of what? That. So when we integrate the x, we are going to get what? We are going to get x. Then we add the constant of what? Integration. So we have, since we are having c1, let's make this one what? C2. And then we integrate du all over e exponent negative u. Nowadays, we can write it as 1 over e exponent negative u du. And we can further write it as what? E exponent what? U. Negative reciprocal in indices. So we can write this as that, then we have what? Du. Now when we integrate u with respect to u, we are still going to get what? E exponent u. That is exponential. We repeat this one, then we take the derivative of the exponent, we divide it by what? That. So u, when we differentiate u with respect to u, get 1. So we are still going to get u exponent u. So when we integrate this, we are going to get e exponent u. We can still add our constant of integration, but still a constant plus a constant will give us a constant. So we just pick only one of the constants. I guess you understand it now. So let's make C2 the subject. So we have our C2 is equal to e exponent u minus what? X. So we have another equation, which is another solution. So you can see that we are having two solutions, which is this one, C1, and then what? C2. And then whenever we have two solutions, we merge them, we put them together to form one solution. And this is how we do it. One becomes a function of the other. So it is either C1 become a function of C2 or C2 becomes a function of what? C1. So we can either use C1 becoming a function of what? C2 or C2 becoming a function of what? C1. Now, since we are having the u, the dependent variable, in C2, let's make C2 a function of what? C1. So we are going to pick this one, C2 a function of C1. So C2 we had e u minus x is equal to a function of what? C1. C1 we had y all over what? X. We want to make u the subject, right? So let's bring this x to the right hand side. We have u is equal to a function of y over x plus what? X. We are making u the subject and we have a e on the u. So let's take the len on either side of the equal sign. So we have len, so that this len you cancel the e. We are left with what? U is equal to len f at y over x plus what? X. So our general solution, which is in terms of, or which is a function of x and y, let's write it as this, is giving us u of x and then y is giving us that. So this one becomes our general solution, our general solution. So this is our general solution. But realize that we are being given an initial condition of what? U of x comma x squared is equal to x. So you have to find the particular solution. This one is our general solution. So you find the particular solution. So with the particular solution, what we are saying is that whatever we see x, we plug in x, whatever we see y, we plug in what? X squared in the general solution. So we say that x is equal to x and then y is equal to what? X squared. So we are going to plug this into the general solution. So we are going to have our u, x, and then y we have what? S squared. So we have s squared is equal to, we have len of the function, wherever we see x, wherever we see y, we plug in what? S squared. So we have s squared all over, wherever we see x, we plug in x. Then we have plus, wherever we see x, we plug in x. Good. So from here, we have our u at x comma s squared is equal to len. Now you can see that one of the x's will cancel themselves, so we'll be left with what? We'll be left with x plus what? X. So this is what we are having after plugging in what? The initial condition x and then s squared for the general solution. Let's continue here. So we have our general solution to be in this raw form. U at x s squared is equal to len of what? F at x plus what? X. And then we have the initial condition u at x s squared is equal to what? X. Since this is equal to that, we can say that this is also equal to that. So we are going to equate this to that. So we have len of f at x plus x is equal to what? X. Very, very easy and then simple. Now let's eliminate the len by taking e on both sides of the equation so that this will cancel this. So that you have f at x plus x is equal to e exponent what? X. Let's make f at x the subject. So we have our f at x is equal to e exponent x minus x. So after reaching this real point, what we are going to do here is to go back to the general solution. So this is the general solution. Where is it? So this is the general solution. We are coming back here and then pick what is in the function f at y over x. We are going to pick this. We are going to do what? Pick this to replace what? X. Wherever we see x, we are going to substitute y over x. We are picking what is in the bracket to represent x. So wherever we see x, we are putting in what? Y over x. So we are going to have a function of y over x, because we are saying that x is equal to what? Y over x. So we have y over x is equal to e exponent x is what? Y over x. Y over x minus x is equal to what? Y all over x. So after plugging in this, we are going to replace this in the general solution. We are going to replace this in the general solution, because in the general solution we have f at y over x, and we are saying that f at y over x is equal to this. So we are going to replace this in place of what? F at y over x. Very, very easy and then simple. So you go back and write our general solution as this. Xy is equal to, we have ln, and then f at y over x is the same here. F at y over x is equal to, so we are going to write this y exponent y over x minus y all over x, and then the last one is what? Plus x. So we have plus x. So therefore the particular solution, so this becomes the particular solution. The particular solution to this semi-linear quadratic problem is what? This. Very, very easy and then what's simple. Let's look at another example. So let's look at this particular example as well. We want to solve for the general solution of this semi-linear PDE. We can see that what makes this PDE a semi-linear is what? This, because the non-linearity is on the dependent variable u. So this is what? A semi-linear PDE, and we are going to make use of what? The method of characteristic equation to find the general solution. With this one, there is no initial condition given, so it is very, very easy for us. So let's have our solution. So first we have to identify our a from the equation. Our a is the coefficient of ux, and then our b is the coefficient of uy. So we have 2xy, and then our f is the function on the right hand side, that is what? U squared. So after having this, we write your characteristic equation. So we have dx all over a. Our a is what? X is equal to dy all over b. B is what? 2xy is equal to du all over f. Our f is what? U squared. Since our f is not equal to 0, we are going to form two equations. So first we are going to start with dx and then dy. So we have our first equation. We are going to pair dx and then dy. So we have dx is equal to dy all over 2x y. Very, very easy and then simple. We want to separate the variables into dx and then dy. So let's multiply both sides of the equation by x so that we can cancel this x from it, so that we have dy all over 2y. I believe you can see that. So we have x times dx all over x is equal to x multiplying what? Dy all over 2xy. So from here we can see that this x will cancel this x, and then this x will also cancel this x. We are left with what? Dx is equal to what? Dy all over what? 2y. So from here we can decide to multiply 2 by 2, so that we have 2dx is equal to dy all over y. Even better still, you can even integrate it straight. You are going to get the same answer. So let's multiply 2 by 2. We are going to have 2 dx is equal to 2 times dy all over 2y, so that these two will cancel these two, and we'll be left with what? 2 dx is equal to dy all over y. Let's continue from this side. So we have 2 dx is equal to dy all over y. Now from here we have separated the variables, and therefore we can integrate them. So when we integrate 2 dx, we are going to get what? 2x. Then we add our constant of integration. So we have c. Since we are going to have two equations, let's call this c1. So when we integrate dy over y, we are getting what? Ln y. Since we haven't ln here, let's take the ln on the constant as well. So we have ln, so that this ln and ln go away. Okay. So we want to make what? c1 the subject. So we have our 2x is equal to ln y minus what? Ln c1. We have our 2x is equal to, apply our basic knowledge in logarithms. Since we have ln and ln, we can pick one of the ln we divide their argument. So we have y all over what? C1. Now let's take y on both sides so that we can cancel the length. So this will cancel the length. We are left with what? Y exponent 2x is equal to what? Y all over what? C1. We want to make C1 the subject. So you can say that our C1 is equal to y all over y exponent what? 2x. And we can write this as C1 is equal to y y exponent negative 2x in an indical form. Now we have one of our solution which is either this or that. This or that. Since we are having our f not being equal to 0, we are going to form another equation. We are going to pair this with any one of this. So we have du over u squared and then dx over x. Now you see that when we pick this and this, it will be very difficult for us to integrate when we pick. Some of you are not seeing what I'm saying. If you take du all over u squared and then dy all over 2xy, you can see that we have x here. We can't separate the variables, so we can't pick du and then dy. Since we have x here, why don't we pick dx and then du, so that it will be very easy for us to separate the variables. So we are picking what? Dx all over x is equal to du all over what? U squared. So once we read this point, we can integrate both sides since we have separated the variable. When we integrate dx over x, we have length of what? X. Then we have a constant. Since we have c1, let's make this one c2. Now you can decide to take the length on the constant c2 as well, since we have length x1, length x here. At the end of it, we are going to get the same solution, even though that the phase of the solution or the final answer may change small, but it's still going to give you the same answer. So I will not take the length on that. You can take the length on that. It's still going to give you the same answer. And then when we integrate the u all over u squared, we can write this as the integral of u exponent negative u du. I believe you agree with me. And since we are integrating u with respect to u, we are going to apply our basic integration. We are going to have u exponent negative 2 plus 1 all over negative 2 plus 1. And that is going to give us what? U exponent negative 1 all over negative 1. And finally, we are going to have negative 1 all over what? U. So when you integrate du over u squared, we are going to get what? Minus 1 all over u. Very, very easy and then simple. So from here, let's make C2 the subject. So we are going to have our C2 is equal to minus 1 over u minus what? Length x. Very, very easy and then simple. So we can just factorize our minus out, so that we'll be left with 1 over u plus what? Length x. Very, very easy and then simple. When we expand, we are getting the same thing back. So this is one of our solutions. As I said, we are going to get two solutions, C1 and then C2. Since we are having two solutions, we are going to make them to form a single solution. We are going to put them to form a single solution. It is either C1 becomes a function of C2 or C2 becomes a function of what? C1. Since we are having the u in C2, let's make C2 a function of what? C1. So we are using C2 becoming a function of what? C1. Our C2, we have negative 1 over u plus ln x is equal to a function of, let's pick this one, y exponent negative 2x. So what we are going to do here is to multiply through by the negative. Let's continue from here. So we are going to have 1 over u plus ln x is equal to minus a function of what? Y exponent negative 2x. We want to make u the subject, so let's bring this to the right hand side. So we have 1 over u is equal to minus f y exponent negative 2x. This will give us minus ln what? X. we want to make what? U the subject. So let's do some small algebra here. We are going to have 1 is equal to minus f y exponent negative 2x minus ln x. Then all this is multiplying what? U. We are just multiplying through by u. Now once you have this, we divide both sides of the equation by this. We divide both sides of the equation by this, so that we can make u the subject. So we are going to divide both sides by this. And when we do that, we are going to have our u is equal to what? Is equal to 1 all over minus a function of y exponent negative 2x minus ln what? X. Now we can even factorize the negative out. So we can say that our general solution is going to be u at xy is equal to, let's factorize the negative out. We are going to have negative 1 all over what? A function of y exponent negative 2x plus ln x. Very, very easy and then simple. This becomes our general solution to the semi PDE given. So this becomes our general solution to that. Very, very easy and then simple.